Okay, so last but certainly not least, we have our panel on scaling with moderator Tracy Livengood from Pluto and panelists Zac Williamson from Aztec, grjte from Polygon, Marcello Bardus from Herodotus, and Toghrul Maharramov from Scroll.
Cool. Hello. Thank you.
Hello.
Hello. Nice to meet everyone. I'm Tracy. Cool. So today I thought we could maybe spend a bit of time focused on the prover role in scaling. I think a lot of ink has been spilt on the sequencer, but not a lot of conversation happens about the lonely prover that tends to sit in a back room on some AWS server. So maybe we could talk a little bit about that role and some of the challenges and interesting pieces there, and then open up for questions toward the end. But before we start, maybe we could go through a round of introductions. Briefly, I'm Tracy. I'm the co-founder of Pluto. We're a company working on making snarks just generally more accessible for application developers. And maybe we can just go through everyone.
Hey everyone, I'm Zac. I'm the CEO of Aztec, and yeah, our gig is privacy, making Web3 private.
Hello, everyone. My name is Toghrul. I do research at Scroll. We're building a zkVM-based ZK rollup.
Hello, my name is Marcello. I'm a co-founder of Herodotus, and we are making on-chain data accessible for smart contracts.
Hi, I'm grjte. I am the engineering lead at Polygon Maiden. We're a ZK rollup focused on improved scalability and privacy and extending the functionality of the EVM.
Awesome. So maybe the first place we could start is on hardware. So I think the prover's classically like a hard problem. It takes a lot of compute to generate proofs for the rollups. And today the rollups are probably the largest consumer or generator of ZK proofs in the world. So they're focused the most on accelerating these proofs, and it costs them money to generate them. Maybe you guys could share, just like for those of you that are generating a lot of proofs, like what are you doing for hardware? Do you have a strategy? How are you thinking about it?
I can start because I think my answer is going to be the easiest one. Because when you're because the focus of what we're doing is privacy, a lot of the proving has to be done client side in order to prevent secrets from leaking, which limits the hardware you're using to whatever commodity hardware your user's running. So that's very much the bottleneck for us, and it limits things like using custom silicon. So the best that we can work on with our execution environment really is web GPU. So yeah, for us, kind of, it's all about the proving system and the abstraction layers that you place between the proving system and the developer writing the circuit. That's where we can move the needle.
Fortunately for us, a lot of proving has to be done by the provers. We can't really outsource it to anyone. We currently use a GPU prover. We're exploring ASICs, but we're not really sure if ASICs is the right path just because of them being a bit of a centralization vector versus GPUs where you can get in any store.
Yeah, I think it really depends how the proving is going to look like, because in the case of ASICs, or if we go to the direction of GPUs, like definitely the way how we prove things is gonna differ a lot.
We have explored GPU implementation somewhat. We're actually looking at, similar to what Zac said, web GPU options, and we have a metal implementation inside of Winterfell to speed things up. So we're leaning in on consumer hardware because we do offer client-side proving as one of the parts of our system.
Cool, makes sense. Feel free to go in any direction you want with this. It doesn't have to be too structured. Yeah, I think that's an interesting segue into decentralization. So the deeper you go in hardware, if you have an ASIC that a consumer maybe doesn't have in their household, it means you need specialized hardware to generate the proofs, and maybe you can't get anyone else to play that role. How do you think about the trade-offs between that and decentralization?
I could start.
Are we all going to have prover ASICs in our phones, and the problem's not going to be a problem?
Yeah, no. That would be nice, but I guess there are some interesting trade-offs that you can make when it comes to decentralization and proving, because ultimately when it comes to the resource costs of your prover, like the physical cash amount that your prover costs to run, generally for a blockchain network, these costs aren't that significant relative to the economic value going through a network. Or at least if they are, you've kind of got a bigger problem than your tech stack, because they ought not to be. So like, for example, like, look, let's say you want to scale Ethereum, and you're going to use a zkVM. Then the cost of your zkVM proof might be very large, but you're comparing that against the cost of every single Ethereum node across the entire world running the same computation. Which means, I guess what I'm trying to get at is that parallelism is a very, very powerful tool to speed up provers. And so when it comes to that, and that can dovetail nicely with decentralization, because you don't necessarily need just one prover to make your block. You can split your block up, proof circuit up into multiple sub-circuits and kind of have a tree-like structure where you have a basic unit of compute that every prover is computing, and then you use recursion to kind of aggregate those proofs together. What you lose there is latency. So so I think what the real trade-off space is not really between like the decentralization and the centralization of proofs. It's between the latency of the communication costs between your proofs and the quality of the decentralization you get as a result. Anyway, yeah.
Just to follow up on that, at least from our perspective, decentralization of provers is not important from the perspective of redundancy. It's also important for redundancy, but it's more to increase the throughput of the protocol, because let's say if you prove the block sequentially, then currently our proof times are longer than our block times. And therefore, if you continue doing that sequentially, your finality times are just going to get longer and longer. And therefore, it's much easier to just assign proving duties of different blocks to different provers and do that in parallel, and then have them post the proofs on chain, aggregate them, and then verify the aggregated proof on chain. And therefore, decentralization is more of a way to increase the throughput of the protocol. So you can say it in a similar way that how Celestia does it with the DAS Lite nodes. Basically, the more sampling nodes you have in the network, the larger the blocks can be. And the same thing here, the more provers we have in the network, assuming no other bottlenecks, the higher the throughput can be.
Maybe to add on that, I think there are two main ways we can look at like splitting proving. So you can either aggregate on-chain all these proofs, and also you can aggregate them off-chain and create a tree-like structure. But that also leads us to another problem, which is basically how we orchestrate that proving. And that's also another question, like should we select one leader and that leader says, you prove this, and you prove that, or we go for a fully on-chain approach and we just merge the proofs together on-chain, actually the results.
Yeah, I think that's been an often topic, or like a small topic of discussion in decentralization is, how do you choose the leader? How do you choose who's going to actually be in charge of generating proof for a given transaction, set of transactions, or block? What have you guys thought about in terms of decentralizing that role and having an economically viable game that gets played?
I can tell you what you definitely shouldn't do. You shouldn't use proof of work style system.
We're not going back to mining.
It's not even that. It's like, at least in mining, you have some form of randomness. So essentially, your probability of winning the puzzle is relatively proportional to your hash rate in the network. Whereas in here, the most efficient prover always wins. And therefore, it basically has a significant centralizing vector long term.
I think there are other structures that people have explored versus like a race to the fastest proof versus like a stake-based leadership election. Have you thought about this trade-off at all?
We spent quite a lot of time thinking about it because it's a serious problem that whether you staking doesn't help, because if you just require stake, because what you're really, if you're using stake, then who are the stakers? They're the block producers, and you just get a secondary market for proving. And you really don't want a winner-takes-all economic market for proving, because that will then lead you to just having one prover that runs your entire network or proves your entire network. And even if the prover doesn't have to be trusted, because they can only either make the proof or not, it has a huge centralization. It has an infrastructure risk, because if that prover goes offline, you've got problems. If that prover is forced to go offline, because they're running on AWS and Amazon gets coffee and they're like, you're violating our terms of service, then you've got a problem. Oops, sorry. So yeah, I think it's very important that the network has an economic model which incentivizes at least two provers And one way you can do that is basically is again through parallelism, because if you break up the work that needs to be proved into a large number of blocks, and they're all getting constructed in parallel, then at the very least, say if you have 512 compute units, then the best prover needs to be 512 times faster than the second best prover for them to get capture all of the economic value. So you get some useful effects there.
Maybe you could go a little deeper on that. So you talked about splitting into 512 different provers, each one needing to maybe prove a single transaction, and then how do those come back together?
Yeah, so to give an example with Aztec, although I'm not sure how applicable it is to the zkVM, is that you have a roll-up circuit that aggregates 2 user transactions. And then you take another circuit which aggregates 2 roll-up proofs. And then you take another circuit which aggregates 2 of those in this tree-like structure, so where it's always 2 by 2 by 2 by 2 up until you get to just a single proof that verifies everything. And that means that there's basically just a lot of parallel compute that's up for grabs. So even if at the protocol level you don't just define who is making those proofs, assuming an efficient market, a secondary market will turn up to service the block producers. And the hope is that you will get more than one prover, although I do think it needs more refinement, because it's not just about how fast the prover is, it's also about the costs for them to make the proof and the marginal advantage that they have over other provers. So it is a tricky, very tricky problem.
But I feel like that's where staking might help, actually. So let's say if your goal is to incentivize as many provers as possible, what you can do is require them to stake a certain amount. And then if a proof is not submitted within a certain period of time, let's say 5 minutes, 10 minutes, you slash them or you slash a portion of their money. And therefore, no one is incentivized. There's no incentive to run just one prover because you're unable to submit all those proofs in time. So it kind of incentivizes decentralization.
Wouldn't a secondary market sort of cause a problem there? So imagine I develop an ASIC. So imagine your network prover network was running on GPUs, and I make an ASIC chip which is way faster and way more cost effective. Then I can basically just act as a secondary market where I can just basically go to all your provers and go, I'll do your proof for cheap. You take some margin and we're all happy.
Oh, you could do that potentially if you have enough compute to be able to do that for everyone. You can potentially do that, but it's unlikely that the prover market is going to control all the slots. It's likely that some of those slots are still going to go to other. So it's the same thing as liquid staking. Even if like Lido has a significant control over the network, it doesn't have 100% control. And I think the same would be true here.
What's the thing is, what is directly connecting a staker to being a prover? As in, why can't they just pay somebody else to do that?
You could potentially do what Ethereum does and basically embed the signature into the proof, and therefore the only person who could submit the proof is the one who has the signing key to the address that you register on chain when staking.
Yeah, fair enough. That could work.
A slot leader for the proof generation, essentially. Cool. Maybe we could shift a little bit. I want to. I have a question on. So yeah, I'm curious to hear sort of Toghrul. Like, I've seen work from Scroll on like the roller network. A lot of, I think, L2s today are focused mostly on the sequencer problem. They're talking less about fraud proofs and less about the prover. It seems like Scroll's put some time into the roller network and they're thinking there. How do you prioritize between those things, or like vaguely, how do you prioritize between those things?
We don't actually prioritize. We work on both in parallel. It's just we write less about sequencers because we're less convinced on what path we're going to take in terms of sequencing, and therefore we just don't talk about it that much. So in terms of the prover, as I mentioned before, it's needed not because redundancy is important or something. That's important as well, but it's a pressing issue because we somehow have to parallelize the proving. And the easiest way to do it is by decentralizing the network and allowing multiple people to participate and submit proofs in parallel.
And maybe for grjte, I'm curious to hear about, and sorry if I pronounce your name poorly, but it's a difficult one. So Miden is kind of a new take on some of these challenges. It's not an EVM-based rollup, and I think it's been a bit of a ground-up rethink. What about that excites you? And what do you think are some of the cool new opportunities that Miden opens up?
I think Miden has leaned really hard in on parallelism and the opportunities there to scale computation. So we are doing this same model that Zac was talking about of doing transaction proofs and then batching them together and then aggregating the batch proofs into block proofs. But we've also we've adopted this note-based model instead of having a strict account model where I send you a note and you have to actually consume that note. So it's 2 transactions for me to send you some amount of money. And what that means is that you can do that proof locally yourself. I can do that proof locally myself. And that opens up a lot of opportunities for parallelism. It also opens up a lot of opportunities for privacy, enhanced privacy. And so that's something that I think has been a really big rethink that Miden's leaned into. Another thing I guess I would add is that we're looking at reducing state bloat as well. And one way to do that is to let users maintain their own state locally. So shared state still has to be on chain, and we still have to have all of that for data availability. But if you want to keep your state private, you can keep your state off chain. And you have to be able to provide it when you do a new proof to update your state. But that means that the state on the chain doesn't actually have to grow at the same speed, at the same rate as it currently does.
Got it. That makes sense. So you can have just the commitments on chain maybe, but the full decommitted.
Right. In any shared state,
yeah,
that still has to be.
Cool. Yeah, Miden's an interesting programming model. I think it's pretty exciting. Cool. I don't know how much time we have. Is 10, 15 minutes, or we have 10 minutes? Okay. Let's do maybe one more question, and then we can ask the audience. So let's maybe think a bit about the future. L1 today, if you look at mainnet Ethereum, I think all of the teams here are kind of depending on that infrastructure in some way. It plays a diverse set of roles. It verifies proofs from the rollups. It serves as a data availability layer. User applications use it. What do we think the role of L1 ends up being if we look forward a year or 2, maybe even 5, if all the rollups are successful sort of in their journey?
Composability layer between different L2s. So essentially, all the rollups would use it to post data and finalize the state, and then compose with one another. And also, probably some of the tokens are still going to live there, because it makes sense if you want to have your token be moved around different L2s. It makes more sense to deploy it on an L1 rather than on a specific L2.
Yeah, we believe that L1 will always have a monopoly to basically be used as an exchange for commitments from all these different rollups, which eventually will always lead to some delay when it comes to accessing data across all these rollups. And that also leads us to a layer where we finally verify all the proofs.
Yeah, not much to add really. I mean,
Any divergence of opinions?
Well, I think L1 will become the canonical store of value because for the reason you said that it's useful to have composability between of like the same asset on multiple different rollups. But there's a kind of a if rollups are successful, it's almost inevitable that basically the L1 will just become the point where the rollups are finalized and data is posted. Or that might even go to another layer. Because the economics will mean that it'll be somewhat too expensive for individuals to transact, because they're not competing against other individuals, they're competing against rollups, submitting batches of thousands and tens of thousands of transactions.
Yeah, rollups will own the block space for sure. They have a lot of valuable stuff.
I think they already use up a significant percentage. Of course, with 4844, that percentage is going to decrease. But if we assume that going forward, more rollups are going to pop up and more are going to start posting batches and settling on the L1. You'll have more proof verification, more use of storage for like storing state, withdrawal trees, etc. So the use is just going to grow and grow the percentage relative to like the user.
Awesome. Maybe we could open up for questions at this point. Thank you all for your.
So my question is, what is a layer 2? And do they exist today? I'm sorry,
All right,
I
we
had
can
to
all
do it.
at this point we can all leave.
I'm very sorry.
Roll-ups aren't real.
Yeah, they're all sovereign. No, they're not. All right, should we go into the whole social consensus thing, or should we go with the L2beat definition? So L2beat defines it as a layer that uses the underlying layer for correctness without relying on the honest majority assumption. I think it's not a complete definition because there are certain things that are missing there. So for example, there was an argument a few weeks ago whether protocols that require an honest majority assumption for liveness, should they consider it to be L2 or not? And I'm of an opinion that I think it's fine for the liveness to rely on honest majority assumption as long as the correctness doesn't rely on it. So yeah, we still don't really have a generally agreed upon definition. Sadly, Patrick McCory is not in the crowd. He might have probably expanded on it.
I do have more in my arsenal if we need. We can keep
Hey guys,
going.
way in the back over here. So if, hypothetical scenario here, if Gnosis Pay takes off and starts dominating block space over all the L2s because it has so many transactions being processed through it, then what is the role of L2s versus having alt L1s like Gnosis Chain connected with trustless bridges?
But there's no such thing as a trustless bridge.
I have more of a question, just following up what you said, that there's no such as a trustless bridge. Why isn't there such thing as a trustless bridge? Because an L2 to an L1 bridge is this trustless bridge.
It's trust minimized. So the way I like to explain it is this way. So you have your ETH on Ethereum. You run a full node. It doesn't matter what the network does. They can never steal money from you because if even the majority proposes an invalid block stealing your money, your node will always just reject it. Now, let's say that a rollup that uses, let's say fraud proofs for now. ZK is great, so we're not going to slander ZK here. Fraud proofs, and for some reason the incentives are broken, so no one's following the chain. And somebody submits an invalid state, and nobody challenges it, and that person just steals your money, and you run an Ethereum full node, but your money is still stolen. So essentially, you're making an additional assumption that there's someone running an L2 node capable of submitting a challenge in time in case somebody tries to steal your money. And the same is true with ZK, but the assumption is a bit weaker. You need to assume that the zero-knowledge proof system that is used is actually correct and doesn't have any vulnerabilities that allow you to steal money. So that's why my argument is that there's no such thing as a trustless bridge.
Yeah, I'm going to keep harping on this a bit more. Actually, if you do run a full node, you can get Eclipse attacked, in which you believe that you do have some funds, but actually you don't. So what is your response to that?
But Eclipse, so the assumption that you have at least one honest connection is the core assumption. You need to make some assumptions when you run a full node that, for example, the signature scheme is running correctly and no one can fake the signature, or the hash functions are running correctly. So trustless doesn't mean that there are no assumptions. It just means that there's a base level of assumptions that you can not get away without having. And anything else on top of that means that you're adding an additional assumption, which means that it's no longer trustless, it's trust minimized, or trusted if it's a strong assumption.
So if we look at running a node as the base layer of a trust assumption, that you do need to have a honest party in the mix, how is that different from a bridge that also requires a honest party to be in the mix?
But now you have two honest parties to trust, which is more than one honest party.
Say again?
So now you have two honest parties to trust, one on the peer-to-peer network side and one on the, if you were talking about fraud proofs, on the challenger side. Whereas if you run a full node, you just have one honest party to trust, which is on the peer-to-peer side. So it's, by definition, you have more assumptions here.
Maybe my math is broken, but it's entirely on-chain, right? It's just one person who has to submit this fraud proof, as it were.
Yeah, but that doesn't have to be the same person as who's running the P2P network. So those are two separate tasks. So those are two separate assumptions that you're making.
I'm just going to stop now.
Maybe we could catch up afterward on how to define an L2. Any other questions in the audience? All right, I think we can wrap up. Everyone has survived the day. Congratulations.
Thank you.
It's been great.